Steinhauer here, welcome back. We're continuing our discussion of post-main sequence evolution. What happens to stars after they leave the main sequence? At the end of the last video, we had gotten the sun to run out of hydrogen in the core, have that core region, which is no longer generating energy, begin to contract, having all the other shells above it contract on top of it, all of them heat up. Hydrogen fusion gets stronger and faster in regions where hydrogen was fusing before, and regions where it wasn't fusing before are now hot enough and dense enough that it can. All of this leads to more energy being generated and the sun moving generally up on the diagram, and that increase in energy pushes the outer part of the star outwards, and that decreases the surface temperature of the star, and the sun will eventually move up and to the right on the HR diagram slowly as the mass of the helium ash core grows. The contraction will happen more and more. The luminosity will continue to go up, and the size of the star will continue to go up, and it will slowly move up the red. This is called the red giant branch. We'll see why in a bit. And stars will move up, becoming more luminous and slightly cooler as they evolve. Now, as this is happening, the helium ash core is getting hotter and hotter and hotter, and eventually something has to give. So eventually that helium core gets hot enough. Well, let's start with this. Eventually it gets dense enough that material is compacted so strongly that there is a fundamental limit which comes into play. And that fundamental limit is called the Pauli exclusion principle. And this has to do with a phenomenon called electron degeneracy. Write that down. So electron degeneracy says, quantum mechanics tells us that no two fermions can occupy the same quantum state. That's a lot of techno jargon, but basically what it means is this: electrons are fermions, neutrons are also fermions, they'll come in later, but let's think about electrons now. No two electrons can occupy the same quantum state. What does that mean? It means that they can't be in the same place at the same time at the same energy, okay? So two electrons can be in the same place at the same time, but then they have to have different energies. So as you are talking about the densities in the center of this evolved star, it's getting denser and denser and denser and denser. And eventually, all of the low energy states are taken. Like every quantum location in the center of the sun has more than one electron in it. And it has so many electrons in it that the available states to those electrons begin to get filled up. And so if you want to squeeze this soup together more and more tightly, you need to move those electrons up to higher and higher energy levels. And that provides a fundamental limit. So there's a limit to how close and compact you can make and dense you can make this material before it will start to push back. There's something called electron degeneracy pressure, which will prevent it from compacting any more than a certain amount. And this has a fundamental impact on the density profile of the star itself. So, for instance, the helium atoms eventually become so closely packed together that they have basically the same density, pressure, temperature. What do I mean by that? I mean, if you remember the plots we made of the sun, density as a function of radius. So this is the center of the sun, and maybe this is the surface of the sun out here somewhere from 0 to big R. Remember, the density is smoothly varying through the whole thing in a normal star, right? This is what a normal star looks like in a density radius profile. What happens in these evolved stars, though, is that there's an entire region where you can't compact it any more together. And so what happens is, instead of having a nice smooth distribution like this, the density of a high mass star, of an evolved star, will be almost the same for a rather large fraction of the interior of the star before it starts falling off again. And this is because of electron degeneracy pressure, because of this pressure that's holding the star up and preventing it from contracting any more than it really wants to. And the thing that this sets up is the density is the same here. And so the pressure is about the same, the pressure gradient is about the same, and the temperature is about the same in this whole region. And so when the point comes, and again, you're still compacting this and increasing the temperature and everything is going up, eventually you get hot enough that the next element can burn. And when it gets to about 100 million Kelvin, helium can begin burning. But unlike in the beginnings of the suns, where that happened only at the very center, this fusion process happens everywhere in the entire core region of the sun simultaneously, since they've all got about the same conditions. And so instead of almost every other part of the star's evolution being a fairly slow, gradual process, this is an instantaneous process. As soon as you have temperatures hot enough that helium fusion can begin, it begins everywhere at once in the middle part of the star. And this is called the helium flash. And very quickly, we're talking about millions of years for most of these evolutionary timescales. We're talking much, much less than that for the star to completely reorganize itself in the interior part of the star, now that a new source of energy is available to it. So that happens at the top of the red giant branch. The helium flash occurs, and helium begins burning all at once. Now, the structure of the star completely changes itself now, right? So now you have a new source of energy suddenly available to you in the center, right? You have helium now being burned at the center. And that, remember, you didn't have any source of energy, pushes out the outer parts of the star. So you're still burning hydrogen in a shell around there. We make a little, here is our shell where we're burning, the core now, where we're burning helium. Outside of that, there's probably still a helium ash shell that isn't burning anything. But outside of that, there is a hydrogen burning shell. And of course, the outer part of the star, even in this scale, is going to be way out here somewhere, way beyond even this what the scale of the slide can show. So you still have helium burn. You have helium burning going on in the center. You still have hydrogen burning going on in the shell outside of that. And as helium burning begins, it pushes that hydrogen burning shell outwards. And as it pushes it outwards, the density goes down and the temperature goes down. And suddenly you're not burning as much hydrogen anymore. And so even though you have a new source of energy available to you, the total amount of energy that the star generating actually goes down. Ironically, a new source of fuel becomes available and the total amount of energy you're generating goes down. The total amount of energy going down means that there isn't as much energy pushing outward on these shells, and the total outer part of the star will actually shrink back down a bit. Not back to completely where it was before, but a little bit. And so the core expands, the total luminosity goes down, the total surface radius, the total radius of the star goes down, and the surface temperature goes back up again. Here is a plot showing the interior regions of a main sequence star. On the left, you've got the outer part of the star here, and you're burning hydrogen and helium in the core. This is what a star looks like when it's on the red giant branch. We've just been talking about that. You've got an inert helium core where no nuclear fusion is going on, and then a shell around that where hydrogen is burning. And now we're talking about this stage where we're burning helium in the core, and we're burning hydrogen in a shell around that. But this star is going to be smaller and less luminous than the star it evolved from that wasn't yet burning helium in the core. So what happens to the star in the HR diagram? Well, the luminosity is going down. That means that the star is moving down on the HR diagram, and the temperature is going up, which means it has to move back to the left. on the HR diagram. So that generally looks like this. So when you're looking at this diagram, the sun will run out of hydrogen in the core and move up. And as that mass of the helium ash core gets hotter, higher and higher, and as the temperature gets hotter and hotter, it will move up the red giant branch until it reaches the top of the red giant branch. And then the helium flash will happen. And then what happens next is it moves down into the left. Exactly where it moves down into the left will depend on a lot of things, like how much mass is lost in this process and how much heavy element is in the surface to lose that mass. It's a complicated process, but it will end up usually somewhere over here above where it started from on the main sequence, but significantly less luminous and hotter than it was at the tip of the red giant branch. This isn't just a theory. We can actually see this in action when we look at a star cluster. Again, star clusters are really important for understanding how these processes work. There's a great analogy that I heard once that I will share with you, which is like studying stellar evolution is like taking a snapshot of a meadow and trying to decipher the evolution of butterflies, right? We can't actually watch stars evolve from one stage to the next. The time scales are way too long. And so we're stuck with a snapshot. We're stuck with, we can see the butterflies, we can see the caterpillars, we can see the cocoons. If we're lucky, we can see an animal transitioning from one of those stages to the next to give us some clue about what's going on. But that's really all we've got. And so these clusters are like the snapshot of a meadow whose age we know, and we can see all of the different phases of evolution because some of these caterpillars take a long time to go through their evolution, and some of the caterpillars go through it a lot faster. That's the analogy of the different masses of stars. So that's what we've got here. We've got a group of stars that all formed at the same time, but at very different masses, and is going through these stages of evolution in a slightly different with slightly different time scales, right? So we can understand now every single part of this diagram. We see here the low mass stars that are still on the main sequence. We see the turnoff point. This point tells us what the age of the cluster is. These stars are just running out of hydrogen in their cores. We know that the hydrogen lifetime of this star is exactly the age of the cluster. Those stars will move up the red giant branch with an inert helium core as they get hotter and hotter and hotter. As they get larger and larger and more luminous, the core temperature is getting hotter and hotter, and eventually that star right there is almost ready to do a helium flash. You can see there aren't many up here. They evolve fairly quickly when they get to this point in the diagram. You can tell that because there just aren't that many stars there. And so that one's about to go helium flash. When it does, it will move down, and where it actually ends up in this diagram will depend on some things that happen along the way, like how much mass it's lost. But what do we call stars that are burning helium in their cores? We call this the horizontal branch. So we've got the main sequence, we've got the red giant branch, and we've got the horizontal branch, which is what these clusters have for a helium burning main sequence. Why do we call it the horizontal branch? Because it looks horizontal for the most part on these HR diagrams. Here's a couple more examples of globular clusters that are pretty old. The one on the left is an actual HR diagram, luminosity on the y-axis and surface temperature on the x-axis. This is a more traditional color magnitude diagram, and this is apparent magnitude and color, but it's basically the same thing because all of these stars have the same distance. Their brightness is basically akin to their luminosity, at least in a relative scale. So you can see, again, all of those regions. You've got the main sequence, you've got call this the subgiant branch actually, and then but this is still just the stars going through a weird stage after they run out of hydrogen in the core, and how they evolve specifically depends on the details of the physics. Moving up the red giant branch, reaching the tip of the red giant branch, going helium flash, and then immediately coming back down here onto these two horizontal branches, which you can see are very different. 47 Tuc has a very short and blue horizontal branch, whereas this Glabre cluster M3 has a very elongated a horizontal branch. But it's the same thing. It just has to do with the amount of metals that these stars have that contribute to how much mass these stars lose, which contributes to what the true morphology of the horizontal branch looks like. But these guys are all helium core burners, as are all of these guys. So how does the fusion process begin? We talked about these helium core burners. What does that process look like? What is helium burned into? Well, helium burns in a process called the triple alpha process. This fuses 3 helium nuclei into 1 carbon-12 nucleus. And it's called the triple alpha process because these helium-4 nuclei are called alpha particles for historical reasons. Now, this can't happen all at once. We need a series of, again, a couple of steps to make this happen. But let's go through what those steps are real quickly. So here you go. The first step is you've got a helium-4 nucleus, and you smash it with another helium-4 nucleus, and it goes into a beryllium-8 nucleus, right? A helium-4 nucleus, let's just draw these out, has 2 neutrons and 2 protons. So you've got 2 of those. And they come together, nuclear physics happens, and out the other end comes an element that is beryllium. It's got 4 protons and 4 neutrons. And that's beryllium-8. So again, nucleons are conserved. We've got charge conserved. We don't really have to do anything else. Usually there's some gamma ray photon or something that comes out of here, but that's not all that important. The interesting thing is this happens fairly easily, but this beryllium nucleus is very unstable. And so it has a very short half-life. In fact, it wants to be back in these helium-4 nuclei. And so almost immediately, 99% of the time, it will decay right back into 2 helium-4 nuclei because it just doesn't last very long. However, maybe one time in a million, you can hit it fast enough before it decays with another helium nucleus. And that will give you a carbon-12 nucleus. And the carbon, let's just draw this out. Here is the helium-4, and here's the beryllium-8. They smash together. Nuclear physics happens, and out the other side comes a nucleus that has 6 neutrons and 6 protons. And that's a carbon-12 nucleus. Carbon being element number 6, carbon-12 having 12 total nucleons, 6 protons, and 6 neutrons. So that's the triple alpha process. You end up taking 3 of these helium-4 nuclei and fusing them together to make a single carbon-12 nucleus. And that does give you energy out in the end. Okay, we'll come back in the next video and talk about what happens after the sun runs out of helium in the core. Stay tuned.